people in the back, can you see the board actually? Is that okay? Okay, good. Okay, can you hear me? Am I okay? Super. So what I talk about today is joint work with Munir Nice, who's over there wearing the baseball cap, and so I mean, I don't think people understand. People know what higher means and what a complement means, but probably and of as well. But probably the other words are not so familiar. I will make those clear quickly. So first of all, I'll explain this object, and I should say, please come in. Okay, I should say this is somewhat between algebraic geometry and tropical geometry, and maybe even complex analysis, although you won't see the complex analysis here. But I want to start out with the non-zero complex numbers. You know, we all know that we can identify them with the positive reals. Well, actually, the reals cross the circle group by an angle and a number goes to e to the r plus I theta. Or, in fact, actually, I could even view this as actually e to the I theta, but I'll write it this way. And for reasons, for reasons for just how I like to write this, I'm going to write boldface T for the torus, for the one-dimensional real torus today. Okay, so I won't use S1 very much. Now, because of this map, in particular, I'm interested in this map here. We get two maps if we take the complex torus. So C star to the n enjoys two maps, one which I'll call log, and this takes this to r to the n. Simply, you take a point z and you map it to log absolute value z1, and so on to log absolute value zn. And then there's another map called argument, which takes C star to the n to t to the n, and you just take e to the r plus I theta. Well, it's just z goes to the argument of z1, the argument of zn. So it's a coordinate-wise argument map. Now, and so, okay, so this comes up to the. We're all familiar with these, so we don't think about them too much in algebraic geometry because these are somehow real objects. But given a variety v in the complex torus, I'm going to look at log of v. I'm going to give that a name. I'll call this. I'll write script a or script a of v for this. This is called the amoeba. These were introduced by Gelfand, Kapranoff, and Zelevinsky in their book on discriminates and multidimensional residues. And I'm going to get the title wrong, but their book. They were studied before then, though. And then you can also look at the image of v under the argument map, and I'll write this as coa of v, or just simply coa. And this is called the Coamoeba. And Mikhail Passare made this definition and proposed studying these objects. These are the lengths in a variety, and these are the angles in a variety. So it's from an algebraic geometry perspective, that's a rather rude thing to do in algebraic variety, is to pull these things apart. Although, as a real algebraic geometry, I'm not so much bothered by these because this is, other than the fact that this is not the positive reals, this is really an isomorphism of this as a product of two real algebraic groups. And if you, instead of taking log, you just take the absolute value, these are really algebraic maps. So these are objects somehow somewhere in between real algebraic geometry. So the amoeba lives inside of r to the n. So this is inside of r to the n. That's a nice affine space. This lives inside the n-dimensional torus. And since I want to talk about convexity, so everybody knows convexity has something to do with affine structure. The torus doesn't have a very good affine structure. However, what we're going to do is we'll sometimes look at the lifted coamoeba. And I'll just write COA with a hat on it. And this sits inside of r to the n. And I think of r to the n as the universal cover. of the n torus. So and what happens then? This is some periodic object inside of here. Okay. So I've made some definitions, but since we're not very familiar with these objects, maybe I should make some pictures. So let's start out with the line. The line x plus y plus 1 equals 0 in c star squared. So everybody at NIMS knows this example very well already, but I'll just repeat it for you and for everybody else. Well, it's useful to look at the line. Well, let's just draw the real picture of the line. That's pretty much the only thing we can do. So you'll have the x and y axes, and my line will be. Actually, does this show up? Oh, it actually does. That's my line. So what I do is I'm going to compute this log map in a couple of steps. So the first step, I'm going to just take the absolute value, and we'll start. So this will end up. Will be at points in the positive orthant, so I won't draw much of everything else. And my real line will go through it will just look at this because it's just a reflection of a ray coming in. And if you think a little more, which I'm not going to try to do in real time, you find that if you look at the complex points of this line, they fill in this polygon or polyhedron because it's unbounded. And then finally, if you just apply the log map. Okay, well, so the origin under the log map is the point 1, 1, which is actually in the center of this object. If you fill in the log map, you'll get something that looks like this. And these points, and it'll fill in everything in between. In fact, if you want to study this a little bit, in c star squared, this line looks like a sphere with 3 punctures on it. The 2 you see in the third at infinity, and so it's just a sphere with 3 punctures. And what I'm doing is I'm mapping the 3-punctured sphere to R2, where one of the punctures is going to infinity in that direction, the other puncture infinity in that direction, and this one in that direction, and then the sphere is stretched in between. Over the interior, the map is 2 to 1, and these are critical points of the map. Okay, so that's these are in fact the images of the real points where things fold over in themselves. Okay, so that's the amoeba of a line. Let's look at the coamoeba of a line. So for here, well, it's the same line again. And so the coamoeba, it's nice to view it inside of a fundamental domain. So maybe I'll shift this over a little bit so we can. Okay. So the fundamental domain, this will be negative pi comma this will be negative pi, negative pi. This is pi, negative pi, 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 negative pi, pi, and there's the origin. And this will be a fundamental domain. So the first thing to realize is that these real points have constant argument. This has argument, these are points of the form negative, the negative orthant. So all these real points under the argument map are going to map to a single point. This is going to get mapped to the point pi, pi. So over here, it's going to get mapped to this point pi, pi, which is also these other points because this is periodic. And then the other 2 quadrants are going to get mapped to, well, you're going to have x positive and y negative. X positive and y negative, x negative and y positive, and so you're going to get these other points. So we get these points from the real part. And now to figure out what happens for the rest of the line, it helps do a little bit of geometry in the Argonne plane. So we're going to look in the complex numbers. Here's the origin. And I'm going to just think about these 3 vectors. What I have is x plus 1 is negative y. So that means that if I write, so suppose x has positive argument. So the argument of x is here. So this is x. And then I have 1 onto it, and this is negative y. Okay. And what we see here is that the argument of x is bigger than the argument of negative y. And that is bigger than the argument of 1. So there's an inequality here that the 0, which is the argument of 1, is less than or equal to the argument of negative y, and that's less than or equal to or actually strictly less than the argument of x. So the argument of negative y is simply is simply pi plus the argument of y. So we need to shift everything down, and what we discover, this inequality gives us that we're strictly inside of this triangle. And so the Coamoeba lies, part of it, when the argument of x is positive, it lies inside this triangle. And you can check that when the argument of x is negative, it lies inside of this triangle, strictly inside of this triangle. So let me follow my color scheme. OK, so this. Now, this looks like two disjoint triangles, but we need to realize this is a periodic arrangement. And so, in fact, let me just sketch the periodic arrangement here, so you can see, so you get a better view of what this map does. So let me just draw a couple of. There's a grid on the board, but it's a little small to draw in there. So we have this periodic arrangement. What's going to happen? What we have is these points are the amoeba, and if you see, if you move this picture over by one, you're going to get these. Well, I'm not drawing them quite so well. And then the Coamoeba is going to live in these triangles. And in particular, if you look at the fundamental domain, okay. So in the fundamental domain, it looks like we have these parts here, but these are really on the boundary of other parts of the triangle. Okay, so the thing to try to absorb from these two examples is just the following observation: is that in this lifted Coamoeba here, so it's convenient to take the closure, which I'll just, without saying I'll take it. The complement of this is a hexagon, just many hexagons periodically arranged. But now, however, this guy, its complement has 3 components, but each one of these components is a convex set. So there's that structure that one can see if you're told to look for it. Okay, so in fact that's a theorem. In fact, it's 2 theorems that I'll state as one. The following theorem. So let V contained in C star to the n be a hypersurface. Then 1, this is due to Gelfand, Kapranov, and Zelevinsky. It says that every component of r to the n minus the amoeba of V is convex. And this comes from some theorem of complex analysis about holomorphic convexity, and I'm not going to. It's not my area, so I'm going to get it wrong if I say anything more. But Munir knows. So and then the other one is the counterpart is due to Nice. He says that every component of r to the n minus the lifted coamoeba of V is convex. So this feature that we saw in this first example is ubiquitous for hypersurfaces. The complements of amoebas are convex, and the complements of coamoebas are convex. And the point of my talk is to try to explain a generalization of this. For the case of amoebas, it's only a partial generalization, although there's a conjecture I'll make very clear about what we believe is true. And then a generalization of this for coamoebas, which is the work with Munir. So this example, okay? Everybody at NIMS could reproduce this in your sleep on the exam at the end of next week? Okay. So the key to generalizing convexity in this case is to use tools from algebraic topology. Namely, the point is convexity has a homological interpretation. So let me just remind you. So this is a convex set. So I'm going to want X to be contained in, say, r to the n. I want it to be open. Okay, I'd like so if X is open. What you notice if you have a convex set X and you intersect it with the line L, what you notice is that the first Betti number, the 0th Betti number of x intersect L is 1, and that's the same thing as the first Betti number of x. In fact, it's better than that. The first Betti number measures the number of connected components, and this connected component of x intersect L, any point in that is a representative of that connected component of x. Okay. However, if something is not convex, so if x is not convex, then it's possible to have a line L. In fact, it's not convex if and only if there exists a line L, so that the 0th Betti number of x intersect L is bigger than the 0th Betti number of x. And that's just to say that these 2 points, the segment in between doesn't lie between them. So these two, so on L, these 2 points, on x intersect L, these 2 points are not homologous, but they are inside of x. Okay. So I'll make a definition. Well, rather, I want to make it. Enrique's made it, but I'll get to it. So a set. Actually, so here's where I'm going to need the board to come down. So I'm going to, after I make this definition, we're going to go to a little picture story. So I'll make the definition here. So a set X, as before, open in Rn is 0 convex if for all lines L, there's a natural map I0 from, I take the 0th, I'll take reduced homology of x intersect L. This naturally maps to the 0th reduced homology of x if this is an isomorphism. So I should connect this up to what we mean by normally convex. And the point is 0 convex and connected implies it's the same thing as convex. So a 0 convex set is a union of convex sets. Disjoint. Yes? Disjoint union, yes. That's what this is supposed to help. Okay, so now I'm going to need help putting the board down. And well, so it's always useful to look at examples. And so we're going to look at some examples that are a little more interesting to draw than the ones we just did. Okay. Okay, and it'll warm up in a minute, and I'll get to see some stuff. Oh, there it goes. It's coming in slowly. Okay. Let me make these a little larger. Okay. It'll okay. So well, this picture you see here, it's 2 pictures of the same object. It's the amoeba of a line in in space. The line has a complex parameterization. And that's manifested by the fact that the map from the line to R3 under the log is injective. So this looks like a sphere with 4 punctures in it. But the punctures go off to infinity, and it looks like a sort of a version of the Eiffel Tower. So and now the first thing to observe is the complement is not convex. It's just not convex. And in fact, the complement has 2 components. It has this inside of the sphere, which looks like a ball, and this outside, which looks like, well, it looks like the outside. It's the one you're looking at. Now what to notice here is that, okay, so it's not convex, but the line is not a hypersurface. It has codimension 2. So if I take, instead of a 1-dimensional affine plane, a 2-dimensional affine plane, and I intersect it, and I look at its intersection with the complement, you see this one, it's punctured. It has 3 punctures, that affine plane, and you'll notice that this homology is generated by these 3 cycles, and there's no linear relation among them in the. Actually, maybe there is one among the plane. I have to. Okay, but whatever linear relation is there among the plane, there's one. The sum of those 3 is 0, and that's also true. That's the only relation among them when you inject that into the complement. And here's another plane that has just a single puncture, and that has its H1 is dimension 1, and so is that injects into the complement. Okay, so what we have here is there's an injection of these first homology groups. I don't put reduced homology on there because it's reduced only matters in dimension 0. Okay, so that's a line. That's an amoeba of a line, and let's go to the next page, and these are coamoebas of lines. So this first one is the coamoeba of the line you just looked at. In fact, the way I drew the other picture is I drew this picture, and then I just changed R to log absolute value, and I got the picture out of it. It was actually very nice. And if you want to know that this line has some parameterization on the bottom. Now, this is viewing in a single fundamental domain. I'm rotating it so you get a feeling for what it might look like, but it looks a little better if you look at it in several fundamental domains, because you can see how it connects up. Okay, so So here I want to take the closure of the amoeba, which is the amoeba plus these colored lines that are parallel to the axes, and they'll come up later in my talk, and because I want the complement to be open. And this is harder to see, but this set is also has this property that if you take a two-plane and you intersect it with the amoeba and the complement, and you look at its homology, that homology injects in the homology of the complement. Of course, it's periodic, so that there's a little bit of you have to think about that a little bit, just fine. And the key point that'll be helpful for us is that every time if I slice this with a linear space with a two-plane, I'm going to get a bunch of curves in the two-plane, and they're going to all start and end at where that two-plane meets these lines. You know, that's what you can imagine. Okay, so this is. Now it turns out that there are two types of lines in 3-space. There's the general line. At least when you're looking at them in terms of their angles, and there's a general line, and then there's the real line, which is this guy on that side. So this is the line which has a real parameterization, and it has two distinct components in the algebraic geometry sense, although they're connected. And it's nice to see how this guy fits together. So this is a little different projection. This again is 8 fundamental domains, and this also has the same property that I just described. If you take an affine two-plane, you intersect it. That the cycles that you see on that two-plane any cycle on that two-plane which is non-zero, it'll persist into the complement and being non-zero in the complement. Okay, and just for Berendt, I'll give an example of the tropical object here, which is a non-Archimedean Coamoeba, and here it is in 8 fundamental domains. So this is an object which you can define from tropical geometry if you're working over a field. A local field whose residue field is the complex numbers, and this also has the same property. But the fact it has the same property is a simple observation from the theorem we're going to talk about. Is that this object is a union of coamoebae, and the notion of higher convexity behaves well in an intersection, just like normal convexity, which I think is a good property. So that's all I had to show in terms of pictures today. Let's see, this is the up button. Okay, there it goes. Okay, and now it's back to, this is an algebraic geometry meeting, so it should be on the board as much as possible. And that's the culture in that subject. Oh, thank you. Yeah, so I guess for the next 4 weeks it's going to be like this. Every afternoon everybody's going to be resting up to watch the football the next morning. So maybe we should be more careful what we schedule for the next month. So anyways, so there's a definition, and in fact the definition was already foreshadowed pretty strongly. It's due to Enriquez. In fact, I don't know how to pronounce his name. And he says that an open set X contained in Rn is, he calls this K convex if for all affine planes L of dimension K plus 1, the map. So there's a push forward map in homology from the kth homology, and I'll put reduced in here to deal with k is 0, from x intersect L to the reduced homology of x is injective. I guess I didn't say what coefficients I'm working in, but we might as well take integer coefficients because those are the most complicated. So it's k convex if this if this map is injective. So this says that you look at the intersection of x with L, and the k. So L is dimension k plus 1. L normally has no homology, but if you intersect it with a set, there may be some holes in it. Dimension so this is pretty much the only homology you're going to find in here. So if this homology group injects into the complement, so it says that, I mean, in a sense, I mean, here's an example. If you take, here's an example of something which is not convex, a sphere. Okay, take a ball. If I take a ball in R3, this is not one convex because if I look at the intersection with the equator, I get the plane with a hole in the middle, and that has some homology, but there's no but the complement of this sphere it has no first homology because I can take my one cycle here and I can just cap it off. So this higher convexity says something that there are no in some dimensional k size bumps in the space, k dimensional bumps. I don't know how to express it any better. In fact, it is. I think it's rather hard to express other than just this way. But if you look at the pictures and the theorem theorems I'll tell you, it suggests this is really a good definition. So Enriquez didn't just make the definition; he made a conjecture. He says that if V contained in C star to the n has codimension k plus 1, then Rn minus the amoeba of V is k convex. But Enriquez wrote a paper, so I mean it's nice, it's good to make conjectures, but they usually require some theorems if you're going to put them in a paper. So he has a theorem on this, which in a sense, it almost proves this conjecture. In another sense, it's far from it. So here's this theorem. He says that the map IK is injective when restricted to positive cycles, and I need to say what that means. So by a positive cycle, this affine space, choose an orientation of it, and then a positive cycle is one which bound okay. So from that orientation, so you need an orientation that, and those are then cycles which are positive sums of oriented cycles, or rather, the cycles come from boundaries of simplices in L, and that's where the orientation comes from. So however you slice it, so this is true for positive cycles, but not every cycle is positive. The difference of two positive cycles need not have a representative as a positive cycle. I think you can already see that in the line. There's cycles that can't be represented by. I have to think about that, but I won't say anything more. But then there's a theorem. I didn't double check my spelling on this. Bushuevo and Seek. Did I spell her name right, Munir? Okay, his name is right for sure. So what they showed, and so this was I think mostly, well, this is a little bit algebraic, geometric, and topological, his proof. He ended up using intersection theory a little bit, just the intersection numbers. He showed that intersection, since complex varieties are canonically oriented, if you intersect some positive cycles that are supported on complex varieties, you're going to get a positive answer, and that's essentially his idea there. So this used just some little algebraic geometry. This used complex analysis, and they said that if V is a complete intersection, then Rn minus the amoeba of V is K convex. So I'm assuming that V is codimension K, and the codimension K plus 1. And the idea here is that V is the pullback of a map to the complex number to C K plus 1 under a regular map under there, and it's a pullback of the origin of that. And there's a nice form on CK plus 1 which surrounds the origin. Essentially, the normal bundle to V is trivial, and you can use that to write a form which then you do some integration and things pop out. I won't say anything further than that, but this is fairly nice. Okay, so the theorem that I'm going to offer today is, well, we know Enrique's definition now. So this is due to Munir and I. It says that if V is contained in C star to the n is, or has codimension K plus 1, then R to the n minus the lifted coamoeba of V is K convex. And we saw this already roughly in the case of lines in 3 space. Their K was 1. Okay. And now I want to before I rub this out, I want to point out that this question about amoebas is still open. I don't see any way, and certainly Enrique's doesn't. He's much smarter. He doesn't see a way to go from this statement to his conjecture. I don't, and we know for complete intersections, but we don't know it in general. I mean, I should also say that his theorem is somehow 95% of the way there. Maybe not in terms of difficulty, but in terms of the idea. It's very clear that this conjecture should be true, but we don't know how to prove it, or I don't know how to prove it. Okay, so let me offer a simple fact about K convexity. So here's really it's a simple lemma. It says that if x and y are K convex, so is x intersect y. So this higher convexity behaves well under intersection, just like normal convexity does. And that should be, for me, this is a reassuring fact. It tells you that this may not be such a wild idea. And in particular, if x equals Rn minus minus a locally finite arrangement of codimension K plus 1 affine spaces. So that's a mouthful, but what this means is in any compact set, you only meet finitely many of these affine spaces. It allows periodic arrangements. If you take away this many affine spaces, X is K convex, and it's proven from this proposition using the trivial fact that if you take away one affine space of that codimension, the complement is K convex, because it looks just like a K-plane with homologically, Rn minus a codimension K plus 1 affine space looks like a K plus 1 plane minus a point. And that's prototypically K convex. So and in fact, this simple idea with a lemma that I'm going to state essentially, it's the main idea in what Munir and I used to prove this. We also had to use intersection numbers and algebraic geometry and other things, but this is the main idea. It was to reduce it to this. So our tool, though, is the main tool, and we already saw these in the examples that I wrote down. In the Coamoeba that I showed, there were all these straight lines that I said were parallel to the axes that were in the boundary of it. So the main tool is something we call the phase limit set. Of V. And so P infinity of V, it's defined to be the set of accumulation points of arguments of unbounded sequences in V. So V is sitting inside of C star to the n, which is very non-compact. So it has many directions to infinity, and you take the points near infinity of V, and you look at their arguments, and then take the limit of that construction, and that's called the phase limit set. And so we have a theorem which describes the closure of the Coamoeba as, let's see, it's the Coamoeba V union. So now I'll have to say it's this together with a finite union of other Coamoebas of varieties constructed from V. And here W ranges over points of the tropical variety of V minus the origin, or maybe the logarithmic limit set of V. It doesn't matter if you know what those mean. So I'm not going to review tropical geometry here because I want to be done really quickly. But this is a finite union, and so what this says is that the closure of a Coamoeba is the Coamoeba together with points you get from looking at Coamoebas of all the initial schemes of V for people who know computational algebraic geometry or Grosvenor basis ideas. And in fact it's this connection that we exploit. So this result that I wrote down, this higher convexity, even though it's talking about amoebas, which are clearly not, they're not piecewise linear objects, it's proven using tropical methods, because we're able to reduce things to what happens at infinity, and then we have a lot of control over this. Things become more linear than and convex geometric. So let me see. What do I want to say in the next couple of minutes? So I'll say a few things about the tropical variety of V. This has a finite decomposition into equivalence classes. And so what are the equivalence classes? I'll say that U is equivalent to V if and only if the initial scheme U of U of the variety V is isomorphic to the initial scheme of V of the variety V. So this is I'll say this in words because I don't want to get into this too much. But you look at the ideal of V, and you pick, and U, by the way, is a vector in Rn, and for every polynomial, if you pick a direction in space, every polynomial has its support, which are the monomials which occur in it. You can think of as points in the dual in the dual z to the n, and this direction vector you're pointing at, there's going to be a collection of monomials where the dot product of them is going to be smallest, and that's the face which is exposed by that direction. This is the internormal notion, and then you can restrict your polynomial to just that face. So if you do this to all the polynomials in the ideal, given this direction, each one of those polynomials you restrict to a face, you get what's called the initial ideal, and then you can look at its zero set, and that's what this initial scheme is. You can also understand it if this direction is rational. Then you can take a one-parameter degeneration of your variety using a subtorus where it degenerates into this object. So there are many ways, and essentially what you're doing is when this is what you're also doing, because this has to do with tropical geometry and the logarithmic limit set, is you're picking a direction in space and you're looking at your variety very far out in that direction. What does it look like in that direction near infinity? That's what all these things I described are doing to you. Okay, so there are many equivalent ways to think about these degenerations, but this is a fine decomposition in equivalence classes by these initial schemes, and this is refined by a fan. So there's a fan structure on trop V. It's not canonical because it depends upon some choices, but there's a fan structure. And what happens is that if you take the largest, so if you take the largest cone, say sigma of this fan structure, elements of that largest cone, maybe the interior, these correspond to INW of V is just a union of cosets of a, I'm running out of space here, so I'll continue over here, of a, it's a union of cosets of a codimension k+1 torus in C star to the n. So if you take a subtorus and you look at the arguments in that, that's going to be a subtorus of the real torus. And when you lift it to Rn, it's going to be a linear space of rational slope. Cosets of that will just be translates of that linear space. So you have a periodic arrangement of parallel linear spaces of these guys. And so what this tells us is in the coamoeba, so the zero in the tropical variety corresponds to the full coamoeba, and as you start moving through larger and larger dimensional cones in the tropical variety, the coamoeba of the initial scheme gets more and more linear until finally you go to the top dimensional cones, and these are some of the smallest pieces in this decomposition. These end up being in the lifted coamoeba linear spaces that are on the boundary of the amoeba, or the coamoeba, so to speak, and so let's call these I'll just call these subgroups the shell, which is a really bad word because amoebas don't have shells, although some do incorporate silicates into their cell membrane, is the shell of CoA of V. Yes. Okay. So what, using algebraic geometry and some ordinary geometry in this decomposition, particularly the way that if you take one of these objects and then you look at its phase limit set, it's already seen in here. Here's the main lemma. Here's the lemma that we use to reduce it to this theorem that I erased, is that let L contained in Rn have dimension k+1, and C any k+1 chain in L with the boundary of C intersect the lifted coamoeba V empty. So what I'm doing is I have this linear space slicing the coamoeba, and I have a cycle in the complement of the coamoeba in the linear space, which is non-zero in the complement. This is what's needed. So the boundary of this is the cycle, which is non-zero in the complement, because it bounds something that has to meet this. Okay, then and yes, and C intersect. I'm sorry, the coamoeba of V non-empty. So we have a picture of a cycle. Well, we have a disk or some cycle. We have its boundary, and the coamoeba V runs through the middle of this somehow. This implies that C meets the shell of V, And since the shell of V is this union of linear spaces of the correct dimension, we can use the fact that their complement is K convex to come up with a contradiction. So I'm not going to explain. C cannot be trivial in the complement of the shell, so it can't be trivial in the complement of the Coamoeba, and then you get to write a paper, right? So when you prove the main theorem. And that's all I have to say today. So thanks for your attention. I hope you got something out of my talk.